Hello friends, this video on structure of atom part 23 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 22. So the question is, find the frequency and wavelength of a photon emitted during transition from n is equal to 5 to n is equal to 2, that is my polymer in hydrogen. So I know that E is nothing but 2.18 into 10 to the power minus 18 into 1 by n initial minus n final both square. This is the energy, right? You put the values here, so this becomes 2.18 into 10 to the power minus 18. N initial was 5, so my 5 square minus n final was 2 square. So if you solve this, you get minus 4.58 into 10 to the power minus 19. So this much energy is emitted when the electron jump from 5 to 2. If you see 5 to 2, energy has to be emitted, and this much energy is emitted when the electron jump from 5 to 2. Also, negative signs means the emission is negative, that means it has emitted, it has lost more actually. Also, now if we got the energy, we can find the frequency. E is equal to h mu very easily. We know the value of h, we know E, you can find the frequency. Also we define wavelength, this is nothing but hc by lambda. So we know h, we know c, we can find lambda. So with this we can do on your. You define again the wavelength of light emitted when the electron of the hydrogen atom moves from 4 to 2. Similar question. E is equal to 2.18, 18, 1 by n initial square minus n by n final square. So n initial was 4, final is 2. 2.18 into 10 to the power minus 18. Correct? So if we solve this, we get minus 4.0875 into 10 to the power minus 19 joule. This is what you get. This is negative, that means it has emitted. Here also you can use the same formula. E is equal to hc by lambda. So lambda you will get E by hc. I have got the value of E, this value h. Sorry. Lambda is hc by E. Lambda is hc by E. H I know, Planck's constant. C I know, speed of light. E I know, I just found. Put the values, you get 4686 nanometer as the answer. How much energy is required to ionize hydrogen if the electron occupies n is equal to 5 orbit? Compare your answer with the ionization enthalpy of hydrogen. Energy required to remove electron from n is equal to 1. So you are saying that in one case you have to remove hydrogen from n is equal to 5. Second case you are asked to remove hydrogen from n is equal to 1 orbit. Let's see the difference. So the formula says E, delta E to be specific, nothing but 2.18 into 10 to the power minus 18, 1 minus n initial minus n final square. N final is my infinitive here, always. So in case 1, n initial was 5, so this becomes 2.18 into 10 to the power minus 18, 1 by 5 square minus 1 by infinity square. This becomes 0. If we solve this, you get 8.72 into 10 to the power minus 22. In second case, same formula, 2.18 into 10 to the power minus 18. Here n initial is 1, 1 by 1 square. N final is infinity, infinity square. So you solve this, you get 2.18 into 10 to the power minus 18 joule. Let's make everything 10 to the power 18 only, right? So this becomes 0.0872 into 10 to the power. So you see this guy is less and this is more. Thus you can see that to remove the electron from 5th orbit it is easy, to remove electron from 1st orbit is difficult. Correct? What is the maximum number of emission line when the excited electron of hydrogen is n is equal to 6 drops to ground state? So if you see, from 5 it can go to 4, 5 to 3, 5 to 2, 5 to 1, right? Or sorry, it goes from 6 to 5, 6 to 4, 6 to 3, 6 to 2, 6 to 1, right? So these are 5 possible options here. From 5th it can 4 possible options. From 4 it can go to 3, 4 to 2, 4 to 1. 3 possible options. From 3rd it can go to 2, 3rd it can go to 1. 2 possible options. From 2nd it can go to 1, only one possible option. You add all 5 plus 4 plus 3 plus 2 plus 1, you get 50. So if you see here, from 6 it can go to 5, it can go to 4, it can go to 3, it can go to 2, it can go to 1. 5 options. From 5th it can go to 4, it can go to 3, it can go to 2, it can go to 1. 4 possible options. From 4th it can go to 3, it can go to 2, it can go to 1. 3 possible options. From 3 it can go to 2, it can go to 1. 2 possible options. From 2 it can go to only 1. So there are 15 possible options, right? So you see this is also equal to n into n minus 1 by 2. So you see this, if you put the value of n equal to 6, this becomes 6 into 5 by 2, that is 50. So you can write a general formula for the maximum number of emission lines for n is equal to, or for the highest value of n to be n, you get n into n minus 1 by 2, maximum emission lines. Correct? Because it's the AP actually, if you see, right? 1 plus 2 plus 3 plus 4 plus 1 with a difference of 1. This becomes n into n minus 1 by 2. So we have seen that in this case the energy associated with the first orbit is this guy. We have to find the energy associated with the fifth orbit. See, energy associated with any orbit is nothing but some constant by n square, where n is my orbit number. So you can say that energy associated with the fifth orbit is nothing but energy by 1 or by 5 square, because energy of 1 is nothing but 1 here. Correct? Energy associated with the fifth is nothing but energy associated with the first orbit by 5 square. It is nothing but minus 2.18 into 10 to the power minus 18 by 5 square is 25. We solve this, this becomes minus 8.72 into 10 to the power minus 22. Correct? And if you talk about radius, nth orbit is nothing but 0.0529 nanometer into n square. So radius of fifth orbit is nothing but 0.0529 nanometer into 5 square. So we solve this, this becomes 1.3225 nanometer. That's the radius of fifth orbit. Easy to find? Find the wave number of the longest wavelength transition in the Bohr series of hydrogen atom. So in Bohr series, my n final is always 2. You know this? In Bohr series, n final is always 2. I have to find the longest wavelength. So energy in this guy for a jump is nothing but 2.18 into 10 to the power minus 18, 1 minus n initial square minus n final square, so I'll make it 2, right? And this is also equal to, energy is also equal to in terms of wavelength, hc by lambda. And we see everything is constant here. H is constant, C is constant, theta is constant, 2 is constant. Correct? So for max lambda, this has to be minimum, right? This can be minimum when this guy is very close to 2. So the minimum value of initial can be, see the ni can be more than 2, right? 3, 4, 5, 6, 7, like this. I'm saying I want to maximize this lambda. So minimize this. To minimize this, I have to give this guy's minimum value. Correct? So the minimum value can be 3. And that is my answer. I have to find the wave number also. Calculate the wave number actually. So for n is equal to 3, I have to find the wave number. So let's do that. I'll directly use the formula. Wave number is 1.09 into 10 to the power 7 into n initial is 3 square, 9 minus final is 2 square is 4. This is what I get, and that is nothing but 1.5236 into 10 to the power 6 per meter. Or what you can do is you can use this formula only and you find the value of 1 by lambda. That is the wave number. Correct. So the question is, what is the energy in joules? Please note, energy in joules required to shift electron from n is equal to 1 to n is equal to 5. So I have this like this. So n is equal to 1 is here, 1, 2, 3, 4, 5. From here the electron jumps to here. I have to find the energy required. Also, this electron again jumps back to 1 and it emits a light. I have to find the wavelength of the light. So this is the first part. Delta E when it jumps from 1 to 5 is nothing but 2.18 into 10 to the power minus 18. 1 by n initial is 1 square minus n final is 5 square 25. Solve this, you get 2.0928 into 10 to the power minus 18 joule. This is the energy that is required to move electron from n is equal to 1 to 5. And the same energy will be released if the electron jumps from 5 to 1, right? So this is nothing but E will be equal to, energy released will be equal to Hc by lambda. I have to find lambda, and energy is nothing but the same value, right? So I can say lambda is equal to delta E by Hc, if you understand. So the same energy is released when electron jumps back from 5 to 1. Lambda is Hc by delta E, sorry. What is the value of H? 6.626 into 10 to the power minus 34 joule second. C is 3 into 10 to the power speed of light meter per second. And delta E we have in joule, that is 2.0928 into 10 to the power minus 18 joule. So we solve this, you get lambda as 9.498 into 10 to the power minus 8 meter. This is the wavelength of the light emitted when the electron jumps back from here to here.
Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.